After an extended first semester discussion of quantum mechanics and electron locations, it turns out we can streamline things quite a bit in terms of what we need to know. We're worried about chemical reactions, how and why chemical reactions take place, and how particles interact with each other. And so if we're going to look at different particle types, we're going to look at chemical compounds, and then we'll look at different types of chemical compounds, and different types of structures and intermolecular forces and things like that. So the first thing we need to address is what is a chemical compound at the base level. And it's just two or more atoms held together by chemical bonds. Which, of course, brings up an important question, and that is, what is a chemical bond? So we'll address that in a moment, actually. What I want us to first address is, why do chemical bonds form? Why do we get chemical compounds? And there's a pretty simple or straightforward answer to that, all right? So we're going to ask this. I'm going to try and set it up like an outline. I don't really have a great plan for doing so. But, so why do compounds form? We've used this abbreviation before, and we're going to use it again now. Compound, I'll abbreviate CPD to save a bunch of writing. So why do chemical compounds form? All right. Why would something happen? And the short answer is, something's either forced to happen or it happens naturally. And if these compounds are forming naturally, then there must be some energetic advantage to it. And what we have in the case of these chemical compounds forming is we have something reaching a lower energy state. All right. So the key idea here is you have the system reaches a lower energy state. All right. And we're going to take a closer look at what it means to have a lower energy state. But the idea should make sense. Like someone who's more excited, more amped up, less stable, most likely. I always joke with my students that maybe you got somebody who drank a case full of Red Bull. They would be very, very excited, but they would be very, very unstable. And naturally, it would progress from there to a lower energy state. Or when we talked about emission spectra, you have an electron jumping from a lower to a higher energy state, and then it falls back down naturally. Or if in the world of like physics, you have potential energy. If I lift this pen up over time, I think most people would find it intuitive to say that in the long run, that pen is eventually going to go back down, because this is a higher energy state and lower energy states are more probable. So why are these compounds forming? Lower energy states. And you can take a much closer look at that with thermodynamics in terms of entropy and enthalpy, and then Gibbs free energy. So very interesting stuff. But lower energy state. In the case of these bonds, the question is, what is that lower energy state that we're looking for? And that lower energy state for our compounds, at least at the root level, we're talking about a full, and this is an important term, octet. All right. Now, I think you probably talked about octet, the idea of the octet rule at some point in time, but we're going to pretend that didn't happen, and we'll jump right into it here. The octet, I think anybody can look at that word and know octet's got something to do with 8, and we spend a lot of time in quantum mechanics coming up with how many electrons can be in different places and mapping out electron locations. So it turns out 8 electrons is a significant number, because our valence electrons, so this is a full set of valence sublevels. All right? And our valence sublevels, if you think back, are the S sublevel and the P sublevel. That's the S sublevel and the P sublevel. S, one orientation, one orbital, 2 possible electrons. So you've got 2 valence electrons. And the P sublevel, you have 3 orbitals, 3 possible orientations in space for 6 valence electrons. And that gives us, when we add it up, a total of 8 valence electrons. And that is the maximum number, all right? And so when we're talking about a lower energy state, in general, we're talking about 8 valence electrons. I did skimp on my wording a little bit because these valence sublevels are the S and P sublevel of the highest main energy level, right? So All right, so it's not all the S's and all the P's. It is the outermost S and P sublevels. So I guess it would be useful for us at this point to maybe just write out a straight definition of what we have that's called the octet rule, and I'm going to adjust that ever so slightly. But before we do, let's write out a straight up definition of our valence electrons, all right? All right, you've probably seen these in class or in some other context described as the bonding electrons, right? Or maybe the outermost electrons, which kind of makes sense in those contexts because what electrons are going to do the bonding, the electrons closest to the outside. Now, neither of those is our definition, but that's what those electrons are. Our definition is that we have the electrons located in the S and P sublevels, as we said right there, of the highest main energy level. And I'm just going to have a disclaimer here. None of these words are necessary for coming up with compound types or anything like that. I know it seems odd for me to say that. You don't have to know the definition of valence electrons or whatever. We can apply some very simple ideas from the periodic table, and then we're going to be able to literally connect the dots to come up with what these structures are going to look like. So don't be intimidated by all these words, because we're going to trim it down to a few very, very, very basic skills that anyone could pick up, chemistry background or no. Let's jump back here to our octet, that not the greatest highlighter, and our octet rule. And I'm going to change the wording ever so slightly from what you traditionally see. I mean, like, if it's an octet rule, it's got something to do with 8. And generally, you'll see that definition as atoms tend to gain, lose, or share electrons in order to have 8 valence electrons. And that's true, all right? But there's a little more to it, all right? So for our octet rule, that first part's going to stay the same. Atoms tend to gain, lose, or share valence electrons in order to have and I'm going to put in parentheses here in a different color, which you probably see in most cases in textbooks, in order to have 8 valence electrons, when I think it is more appropriate for us to say a full set of valence sublevels. And I think that's okay to say, and the reason I mention it that way, number one, 8 isn't going to be the number every single time we need things, but second of all, there are things that have a full set of valence sublevels without having 8. For example, hydrogen has an electron configuration of 1s1, right? And helium, 1s2, and there is no p, right? So a full set of valence sublevels for hydrogen or helium would be 2 electrons, so it wouldn't be 8. And again, it's just semantics. No one cares. 8 is the number of interest to us in most cases. In fact, that's not even going to be a huge limiting factor later. All right, so we got some of the basic vocabulary out of the way. Why do chemical compounds form? Again, as we look at it, to get to lower energy state, what do we mean by that lower energy state in terms of the electron positions? We're talking about a full octet, right? So that's a full octet, right? A full set of valence sublevels, and that is stable, which is a low energy situation. So in short, why are the bonds forming? Reach a lower energy state.